Awesome. Great. Can I just get a confirmation from someone in the chat that you can hear
Yeah,
me well?
yeah, we can hear you and see
Oh,
everything.
Sure
super.
can.
That's fantastic. Thank you. Great. So, hi everyone. Awesome to be here. I'm a PhD candidate at the Von der Schoor Lab in Cambridge, and I immediately want to just jump into this topic and start off with a simple question. Why should you even care about this? And I think you should care for a few reasons about this prompting and language model. So, one of the first reasons is that in case you're building language systems or you're a part of a team that's building language systems, you want to understand maybe the key areas within prompting that are really driving the main performance gains that are driving most of the innovation. And it's even a bit interesting and strange to say, but many of these innovations are simply nice ways of combining, storing, using, and reusing prompts. So if you can understand some of the key innovations and recent techniques that are developed for prompting, I think you can maybe get a better understanding of some of the drivers of these larger complicated systems, including AI agents and other stuff. And surprisingly, most companies right now are building some sort of AI systems. I think you're not even considered a tech company these days if you're not building an AI agent. So substantial parts of that are fancy prompting techniques. So this is what this specific presentation is about. It's a beginner-friendly presentation, so you're not expected to know pretty much anything. It's very, very easy to start off, the whole summer school. And we're going to be answering 4 questions today. So the first question is, what is the current state of the art in LLM prompting? Then how is this used in current systems? Then can prompting be automated? And yes, so in what ways? And what are some concrete frameworks that you could immediately use after this presentation ends if you want to try out and implement these different systems yourself? So we're focusing on these 4 questions as the guiding point, and I'm hoping to have about 15 minutes. We'll see how it goes at the end of this to just have a Q&A in case you have anything. Right, so let's jump right in. So what are the current state of the art? What's the current state of the art in LLM prompting? So there are 4 main ways how prompts are modulated. So just for the sake of it, let's define a prompt. So when I say the word prompt, I mean an input to a generative language model. It doesn't actually have to be a language model. So more generally, an input to a generative model that modulates or changes its output. And so the idea is that if you change the input in certain ways, you can simply improve or change the output. And so there are 4 primary mechanisms people are currently using to try to see how you can swap the input to get better outputs. 1 is changing the prompt template. 2 is in-context learning. 3 is changing the thought generation process. And 4 is doing more different iterations. So let's go through all 4 of these just to get a sense of where everyone stands. So what does it mean to change the prompt template? Well, in almost all cases, if you're building some sort of language modeling system where you're trying to do something, maybe something like a sentiment classifier, you're going to have prompt template. A prompt template is simply a bit of text where you say you explain what you want to do, and there's a specific room for an input that actually varies. So a prompt template is classify this review as positive or negative, and then the review. And then the prompt itself would be this prompt template with the actual review. And notice if you just add this prompt template, you basically already have an automated system whereby if you just change the review, you can get different outputs. It becomes a bit tricky because you can change the prompt templates for these models to become better and better. For example, you might start adding stuff such that the output improves more and more. But if you're working on, for example, a situation where you have maybe 50 labeled examples, 40 labeled examples, you can easily, what is currently called do prompt hacking. So if you know P hacking from conventional statistics, you can do prompt hacking whereby you change the prompt at the beginning such that the language model is almost always right. So one of the ways to look at these prompt templates is to look at them as almost hyperparameters in traditional machine learning. That if you look at prompts as hyperparameters, you can understand that when you change them, then you can get variable outputs, but you don't want to be changing them 20 or 30 or 40 times because then you might simply overfit to the existing information that you have. And so it's often good to have a validation data set even for that, but I'm going to cover that in just a bit. So the simplest possible thing you can be doing is just have a prompt template. The second thing is in-context learning. What does that mean? So I'm sure most of you know, but just to make sure everyone's on the same page, in-context learning is where you have a language model where you give specific examples or instructions with a specific input and output you want. So here's an example. This is what an in-context learning example prompt could look like in Python. You would have a variable, something like prompt input equals. And so this is a variable where most of the things will be stored. And first you say the task. So the task could be something like classify the sentiment of the given text from 1 extremely negative to 100 extremely positive. And what you do is then you show simply two examples. So you give one example, the movie was fantastic, yada, 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 and you give a rating, and you think that this rating is ground truth. You think that this rating really represents the true label that you want to emulate. And then ideally, you also give a negative or a different example such that you would have some variability. And then once you give those two examples, you can simply input your third text and then ask for the actual rating. So what's really crucial here is that this is also a fixed structure in the sense that now you can put any new text, and any new text will always have these two initial examples as almost a reference. Now, there are many things to talk about here, such as how do you choose good examples, how many examples to choose, and all of these are important questions that I'm going to touch upon in just a second. But the primary takeaway is that you have to handcraft these typically yourself, especially if you're giving a small number of examples for this to be particularly useful. And you want to have as much variability in these different examples as you can. Before talking about some ways how in-context learning actually helps and some drawbacks, I want to quickly touch upon about why this works. So why is it that this in-context learning works? And there's a lot of ways to look at this and a lot of ways to build intuition. The best way is to think that in-context learning is conditioning on a given set of information. So you've probably already heard from your Introduction to Language Models class that what language models do is they sample a token from a distribution of tokens. And what you have is basically you have a prior distribution of tokens you would sample from. And when you give a specific context, a specific input, what basically happens is that you change this distribution, you change the specific tokens or words you're going to sample from. And what this does is this, because you basically had a prior distribution, you condition on information, now you have a posterior distribution. You can think of it as this working as implicit Bayesian inference. If you make a few nice assumptions about this model, you can actually get some pretty nice and neat results. So for those of you who are inclined more in mathematics, I encourage you to read this paper on how you can explain in-context learning as implicit Bayesian inference. In case this didn't entirely make sense to you, no worries. Let's jump into something very practical, which is 6 major design decisions you would need to make when you're designing these in-context learning systems. So the first design decision you want to have is you want to include within a reasonable set as many examples as you can. So for instance, one example, if you're doing something like labeling positive or negative sentiments, would be very poor because you wouldn't showcase the variability in what is a positive and what is a negative example. The idea is that the more examples you give, then the benefit of that is that the more variability you provide, and so the language model could implicitly pick up on the kind of variability you're showcasing. Often this comes at a practical cost. So if you're a practitioner who's practically implementing the system, you also want to make sure that you don't include too many examples. This is for a few reasons, but one of the main ones is simply the cost associated with this. Language models typically, if you're using a paid language model with an API, they're typically paid per token. So the longer the context or the longer your prompt, the more you're going to pay. So if you're giving 20 or 30 examples in a single prompt, what that's going to mean is that every time you classify your make a prediction, you're putting this big long context window at the beginning. And so that will mean it costs a lot of money for you. So you want to balance simply the costs with the possible benefits, and there are financial ways of practically calculating your expected costs with a certain number of examples. What people typically do is they try to see, do you still get performance increases when you add 2 examples, 4 examples, 6, 8, 10? And so you try out a bunch of things, you evaluate it on unseen data, and then you pick the point where the cost is still good enough within your limited budget, but your performance gains are still much better than the alternative. The second design decision for in-context learning is that you want to order the different examples in as of a neutral way as possible. So for example, a good way to order 4 examples would be angry, happy, angry, happy. A bad way to order this would be happy, happy, angry, angry. Why is this the case? Well, remember that because in-context learning works almost like implicit inference, what's happening is that you're trying to pick up on patterns that exist in your given examples. And in this specific case, you have a new pattern, which is first you label all the happies, and then you label all the angry comments. What happens is that now you're introducing an additional layer of ambiguity where you're introducing a relationship that first you're going happies and then you're going angries, when that's not a relationship you actually care about. You would like to ignore this relationship. So disambiguating and removing all possible other explanations of what the label corresponds to is a really good idea. The third decision is trying to ensure that the label distribution is equal. So if you are using language models for something like a classification task, but it doesn't have to be a classification, it can also be any sort of output. You want to ensure that you provide as many examples for all possible cases as possible. If you don't do that, there are 2 main issues that occur. Issue 1 is that you might implicitly condition the model to simply provide the majority output more often. So if you expect that the label distribution is equal, so you have more or less equal amounts of happy and angry comments, but then you include more angry ones, you are implicitly showing that the prior distribution for these angry ones is higher, meaning that it's more likely that a comment is angry than happy. And if that's not what you want, this can lead to problems. Second of all, you increase the variability of in this case, the happy examples. What that means is that because you simply include fewer happy examples, there's more uncertainty associated with whether a specific example is happy or not. So if you include more examples, you simply reduce the variability within each example. Then, needless to say, you want to have good label quality. So you want to make sure that your labels are simply correct. Then you want to make sure that the format in which you are including these examples is as simple as possible. So you don't include very irregular, fancy tokens, fancy symbols. And the reason why this is important is because if you're using an automated system, so let's say you have some sort of prompt, and in many cases, these prompts, they have in the middle of these prompts, they have variables, and these variables are plugged in by other systems. So if another system somehow outputs really gibberish various letters and words that aren't really common, you are then increasing the noise a bit. So it makes sense to use common formats that don't cause any ambiguity within the prompt. And another similar good thing is that if you have very similar type of examples you talk about. So in this specific case, there's an example, I'm hyped, which is positive, and I'm not very excited, which is negative. And they're very similar phrases. However, in case you have 2 examples such as trees are beautiful, which is positive, and YouTube ads suck, which is negative, in that specific instance, what you're happening is that you're not only disambiguating between positive and negative, but you're also giving different context. And so in this specific case, it's a bit harder to understand. Is the positive negative different because of the sentimentality dimension, or is it also because of the themes? So for instance, especially a smaller language model might have a higher probability of thinking that anything related to YouTube is negative and anything related to trees is positive. Whereas that's not what we want to say. We want to simply convey the sentimentality. So spending some time in ensuring that the examples try differing only in the dimensions that matter can help to almost extract the key message away. Okay, so taking a step back again. So we're talking about how to change prompts. So we can change the prompt template. We can do in-context learning, which is to give factual examples, and there are some best practices for that. The third way is to change the thought generation process. So what does this mean? So different prompts result in different behaviors. It's kind of clear if we prompt a model in a different way, we get a different output. But so what has been empirically observed is that some prompts simply outperform others more generally. And because some prompts outperform others more generally, people have been developing different kinds of prompts that can be broadly categorized into three different processes. So they're called decomposition, where you break down a task into smaller steps and you solve those steps. Ensembling, where you ask a language model many, many times, like 10, 15, 20 times, and then you, for example, take an average or you do majority voting. And self-criticism, where you provide a response and then you say critique this response, and then next time you incorporate that critique. So I'm not going to go through all of these techniques, but what I want to tell you, which is quite important, is that there's, in the past year and a half, people have developed massive amounts of different prompting styles and prompting techniques, which in many cases is simply, appending some sort of text at the beginning, at the end, and then following it through. So let me give you an example. Let's go through decomposition. So decomposition, again, is breaking down the task into smaller steps. So this could be as simple as, this is the task, break it down to 5 steps in sequential order. This would be a prompt that would decompose the overall task into smaller tasks. So this is one example, but here are simply a few different techniques that have been developed. They're called everything from least to most prompting to plan and solve prompting to skeleton of thought prompting. And so these different papers, all of which claim state of the art, by the way, all of these papers simply show that you can prompt a specific model in a specific way to get a decomposed task. And then once you decompose it, it's easier to solve it. A very common way to evaluate this, by the way, is on mathematics tasks. So mathematics tasks have this particularly useful property where you have a question. It's non-trivial because it's required to reason multiple times and multiple steps. You typically don't know the answer by heart. And also, there's a ground truth answer. You know for a fact if you're correct or not, because these mathematics questions have direct answers. And a lot of these different prompting techniques are simply evaluated on different mathematics benchmarks to see which one works better. Some techniques in ensembling. So ensembling means, again, in some capacity, using many language models and then combining them on one of the final steps. So when you combine them, what language models you use, how many you use them, what specific prompt template you use, all of these things are different. But the idea is that you're using many, and then and if you use many, you can get a wider diversity of answers, and then you can incorporate and get better results. And of course, you have self-criticism. So self-criticism basically is the sequential process where you get an output, then you say something like, now criticize it, you get the critique, then you say something like, this was your initial response, this was your criticism, provide a new response. And then you get a new response, and then you can criticize that. And you can do this iterative loop over and over. And so there are these different ways of doing this idea. And so some of these ideas are here, everything from self-calibration to self-refine to self-verification. So I want to maybe zoom into one of them just to have a better understanding of what it is that they actually do. So let's zoom in into this self-refine um, idea. So self-refine prompting is a framework for providing feedback to the model to refine its outputs. So essentially what you have is that you have an input to a model, something like, what is the solution to this mathematical equation? Then the model firstly provides an answer and then goes and provides feedback on its own output. Once it provides feedback on its own output, it then takes this feedback in practice and proposes a new solution. And it does that many, many times. So I've implemented this self-refined framework in one of my previous projects. So here's just a very simple example of what this could look like in Python. So there are many different ways of implementing this. So this is just to get a rough idea. So this is a Python function. So Python function is simply used to define some inputs and get some outputs. And what I'm doing here is I'm defining a prompt. So you can see that this is just a string. So string means it's just a piece of text. And what I'm doing is I'm basically saying the following, that the context is this, and I give some sort of external context from another variable. Then I say the target variable or the variable that I'm interested in is this. So I plug in information from external sources that I care about. Then I say, this was my previous answer. So notice I say previous answer equals in previous response, and I plug in the previous response. Then I say critically evaluate the answer and then rewrite it and make sure that to follow the instructions as before. And then I just pass this to a language model as a direct prompt, and I get the output. And this is by no means a good implementation or an efficient implementation, but the idea is that you can simply get an output, then criticize it, then get it back, etc., etc. And the fourth method is iterations. And so this is also shown here that you can actually iterate this many times. So that means that maybe you criticize your answer once, and then it improves a bit, and maybe you criticize it twice, and maybe three times. And at some point, typically the answers already reach some sort of best performance. So further criticizing doesn't really help anymore. This also has other trade-offs. So it has the trade-off of computation versus accuracy. So maybe if you're using very difficult to evaluate systems, it will cost you a lot and it will take you a lot of money. So people typically limit these computations and iterations to only a few, up to 10 typically, steps. And one of the main things is that this is only useful in as much as you can optimize the performance by changing the reasoning process itself. In some cases, the task is so difficult that no good prompt will be able to achieve that. So clearly optimizing this wouldn't really do anything because it's a difficult task to achieve in the first place. Good. So given this, just kind of to reiterate, so we had changing the prompt template, in-context learning, changing the thought generation process, a bunch of ways how you can do the thought generation, and then doing it in multiple times. And people have been combining them up and go. There's no really hard science. It's very much an empirical practice. People are just trying what works and combining them and observing that some things just happen to work more than others. But there are some good practices that you can use. So at a minimum, you should always include your prompt templates in the appendix at the very minimum. And if you're reading any work, you should expect to see the prompt templates in the appendix because this is expected for good evaluation purposes. So I think there's a really good way to actually, if you're using a language model, here's a good tip. If you're using language models, there's a way to get your language model to be correct almost all the time, which is to give the answer in the prompt. But clearly, giving the answer in the prompt is ridiculous. And so you need to show your prompt templates to make sure that you're not, to show everyone that you're doing good, valid, thorough research, and you're not skipping in some way some steps and providing magical answers in your prompts. So what has happened recently is that this idea of prompt hacking seems to have come into play. So this also reduces your ability to, or people's ability to do prompt hacking. And ideally, you want to show a few variations and produce, if possible, sensitivity analysis of are your results really that sensitive to the specific change in prompt? Because if it happens that you get good results only with this specific prompt, and if you change something, everything goes to dust. That's not a particularly convincing outcome unless that's a specific point you're making. So you want to be very transparent in what it is that you're doing. And if you're using a smaller data set, because you can look at prompts as hyperparameters, you would like to consider having a train and validation data set. So if you're using some sort of training data set to optimize your prompts, and then you're showing the results on that same data set that you use to optimize your prompts on, then that is simply over tuning to the data set that you have. So that would be very bad practice. And so it's common to show sensitivity analyses, but even with a specific prompt, results typically differ between different environments and between different data sets. So if one specific prompt might work on some examples, but then if you change the environment suddenly, it might not be the best performing prompt anymore. Good. So the first question we just covered is what is the current state of the art in large language model prompting? And so we said that we can change the prompts to help improve LLM outputs in 4 ways. And then we went through different ways and looked at the different design decisions you make in each way. Good. With this, let's jump to question number 2, which is how are these prompt techniques used in current systems, and how do you use them practically? Okay, so back in the days, which is 1.5 years ago, so this is already back in the days because everything's moving so fast. So back in the days, large language models were chatbots. So you had a conversational system. These days, people are using them in much more fancy ways. And so right now, it's very common to have large language models as a part of a broader system instead of a simple chatbot. This is something that you will see with Sam's presentation just after me, where he's building a much larger system from this idea of prompting. And there are many ways how you can categorize this, but primarily within these larger systems, large language models are then used in 4 main ways, which is they provide information. So you ask information and you get an answer. They retrieve information, which means they don't know the answer, but they can actually go to a specific PDF, go to a calculator, go and search the web and get the answer. They can manage or orchestrate larger processes, which means that you plan out how specifically you're going to solve this task, and then you implement each task independently, and then you decide when you want to go to each task, and you decide and build internal if-else statements. So you can manage and orchestrate these larger processes. And you can ensure correct input-output formats. So maybe your input is always a number, your output is always an Excel file or a JSON file. You can structure the outputs in the specific ways that you want. And you can wrap language models into specific templates with some statements, assertions along the way that can help you achieve these 4 goals. Good. So language models are used typically as a part of a larger system. So it's very, very unlikely that big gains are coming from a simple chat interface. So right now you have much larger systems. And if you've previously listened to Andrei Karpathy, he actually makes a really nice video and talk about how language models are becoming a new operating system and how they're equivalent to or replacing traditional operating systems. So if you haven't heard that before, I encourage you to just go and have a listen. But so what I want to do now is just almost to go through these LLMs within a larger system and talk about the key components. So in many cases, large language systems, when they're being built around these larger systems, what that practically means is that you're building an agent of some sort. And so everyone right now is extremely into large language model agents. And again, I think most tech companies are investing into agents in one way or another, which I think is in one way fantastic. And so these agents have a few different components. They differ from agent to agent. And so, of course, there's no one single infrastructure or one single design that is consistent everywhere. So here it's a blueprint that shows you the key building blocks that most agents or systems have. And I'll explain why these specific components are particularly useful now. So first, there's a memory component. And memory simply means we want to have information that we can retrieve later on. We can have a some sort of planning module where we decide how to specifically execute some number of steps. We can have tools, which means external information, so we don't rely only on the information and the outputs of the language model itself because of problems like hallucination. And of course, we have specific actions that the model can take in response to the outputs it gets from other agents, etc. So you have specific actions you can take. Okay. So what I want to do now is to go through the main components here and to just talk you through what that practically means on an implementation level. So let's firstly jump to short-term memory. So what do we mean when we say short-term memory in a language model? So when we say short-term memory, we typically mean information within a prompt. So what do we mean by that? Well, information within the prompt can be one of two types typically. So one, explicit information provided, or two, previous conversation stored in a prompt. So let's go to the first one, explicit information provided. What does this mean? Well, let's suppose that I have a function, and this function is again in Python, and the goal of this function is to construct a prompt. That's the goal of the function. So the goal is to construct a simple prompt. What you can do is then at the beginning, you can say the task is this, blah, blah, blah. But then you can write, this is the previous information. And then you can pass in specific inputs. And so this would typically be considered as short-term memory in the sense that you've provided some global information at the beginning, and you're always remember that. That global information could be something like how you should behave, act as an expert, act as a judge, act as a comedian. It could be the context that you are operating in this country, or you're dealing with this and this healthcare facility. It can be any sort of other sensitive information. But so it's basically information that you want to remember or information that you plugged in from somewhere else. Of course, you can also have other things such as your previously identified problems in your previous solutions, and then what your task is. So all of this would be explicit information provided. You can also here show the format of your output, right? You can say formatted in this like problem solution kind of way. This is not a really good way to format it, by the way. There are much better ways to format properly language outputs, but I'm not going to be covering them here. Now, another way is what you can look at as short-term memory is simply your previous conversation stored within the prompt. So a really good example of this is if you're using any sort of OpenAI language model, or if you're using Anthropic's language model, Claude, you will be talking with those language models. So what they will have, and what you can do is you can go back to any of your conversations before and just continue interacting. So how come you can do that? Well, that's because all of your conversational history is simply prepended to your current conversation. So this is also a type of short-term memory because you are prepending the conversation that you had as a part of the prompt that you're sending to the model. And of course, this is why as you chat with the model for longer and longer, it becomes more and more expensive for the company because each time you add a specific conversational element, so the overall conversation increases. What companies have been doing to limit this is that instead of including the whole conversational history, they've been either limiting it to the past K conversations. So maybe you would only include the past 10, 15, or 20 conversational elements. Or alternatively, what some companies are doing is because it's really expensive to hold the whole conversation, you simply use another language model to summarize the conversation into a shorter 2-paragraph summary, and then put that summary as a prepending it to the conversation. And then what you can do is you can almost extract most of the information in much fewer words. And that saves you simply a bunch of money. So that's what short-term memory is. So short-term memory is either explicit information or the previous information stored in a prompt. Then long-term memory is typically information that's stored in a specific database or in any specific file elsewhere. So for example, if you are working with patient data, it would be, or with some sort of information like books, it would be quite difficult for your model to always have access to the books, but you can use a retrieval augmented generation system, a RAG system, to on demand take what information you need. So long-term memory is typically, what people mean typically is they mean retrieval augmented generation, whereby you retrieve information on demand from external documents. And this is just an example of how LangChain, one of the frameworks, does it. So you basically take a bunch of documents, such as a long PDF, you chunk it into smaller pieces, then you embed each piece into an embedding space, you put it into a database, and then when you need it, you can perform a similarity search by simply taking something like the cosine distance and then extracting it whenever you need it. If this last part didn't make sense, that's completely fine. The main takeaway here is that long-term memory is simply information that is stored outside of the language model that you can retrieve on demand. Then the next part is, of course, all of the planning and reflection. And this is something we talked about before. There are different ways to decompose, to criticize, or to reflect on all of these solutions. Here's just an example of how you can implement some sort of self-reflection again. So you can have something like a prompt where you say the original context for the task was this, and this was the task. You generated the solution. However, you've identified this issue, and then now find a new solution. And then you can call a language model to get this new solution. And so this would be a self-criticizing implementation. And of course, the big thing that emerged about a year and a half ago, or a year and 8 months ago now, is that language models can use tools, and they can use tools also using in-context learning. And these tools can be anything from a web search to a calculator to retrieving some information to calling another language model. So it's really diverse. Pretty much anything you want to, you can implement as a part of a tool. And this is an example of how one might use a tool. So this is a very common example given for people who start off with this framework called LangChain. So suppose you want to ask the question, who is Leonardo DiCaprio's girlfriend? What is her current age raised to some number? And so what you could do is this language model within it internally could have some sort of input, then it could make an observation, it could extract information, then have an intermediate observation, and then get a final answer. And so this, of course, most of this information is abstracted under the hood in a specific framework. So here specifically, I'm showing, and this is probably not even correct information because the information might be outdated from the retrieval augmented generation system. But if you're interested in, for example, this specific example, this is an old example from a package called LangChain. Everything is abstracted away from you. And most importantly, this uses something called the React framework. So again, kind of the idea is there are many different frameworks floating around, but for a practical user, it's very easy to simply import something through a Python package, implement some tools, and start using them. There's no need to almost define everything from scratch and define the whole logic because people have done that already for you, and you can download it in an open source fashion and start using it. So to summarize this question, so how are these prompting techniques used in current systems? So that's our question 2. And so the answer is that they're typically used as a part of a larger system. And the primary components are memory, reflection and critique tools, actions, or reflection critique, tools, and actions. Okay, let's jump to our third question, which is, can prompting be automated? And clearly it can, but I think one of the main things to talk about here is that large language models are really good prompt engineers. So there's this paper that came out in iClear in 2023, which started off or kicked off this agenda, which was called Large Language Models or Human-Level Prompt Engineers. So what did this paper do and what was it about? Well, they basically said the following. They said that humans can try to tune these language models. You can try to, change different stuff at the beginning. You can say, act as an expert at that. You do this. You can try picking examples. But it's very tedious. It's very time consuming. And to be honest, we're really bad at this. And so they said, well, why can't a language model simply do that? And so what they found is they actually, they can, and they can quite successfully. So this is the framework they provided. And this is, since then, a lot of many other things have emerged. But I want to just walk you through the underlying logic, just to show that it's very intuitive in what it is that these people proposed. So first of all, suppose you have a task. So the task is something like Professor Smith was given the following instructions, and then you got some responses. So the responses are something like the input was proof and the output was disproof. And then the input was on and the output was off. And now you need to understand, well, okay, well, what was the task? What was the underlying task that this person was solving? And so the first thing is that the language model is almost as what they call an inference model. And I think just a really simple way of thinking about it is that it started to raise hypotheses. And so some of the hypotheses you can see are that you write the antonym of the word, or you give the antonym of the word provided. Some worse hypotheses about what this is that you reverse the input, or then that you reverse the order of the letters. So the first thing that the language model does is it provides hypotheses about what it is that you were doing. So this is kind of called large language models as inference models. Then the second step came, which is that they used also the same language models to then score how likely is it that each of the hypotheses is true. So we had a list of hypotheses, which means write the antonym of the word, reverse the input, reverse the order of the letters, and we asked for a number between 0 to 1 on how likely that is. So we got a number. We applied a logarithm function to that, and so they get these green numbers. And then they use a language model to generate even more suggestions, and then they ended up with their final prompts. And so the main takeaway here, and I encourage you to read their paper, but the main takeaway here is that language models can simply be used to infer tasks and to infer information to prepend at the beginning to improve your output. And since then, people have been using this idea that you can use information to prepend at the beginning to improve your output in a bunch of different ways. So there's one really interesting study, which was called The Unreasonable Effectiveness of Eccentric Automated Prompts. And what they basically show is that they use automated prompting evaluators or automated prompt engineers to automate prompts for specific mathematics tasks. And so you had a bunch of mathematics tasks, and you compared two different outputs. So one is how well a language model does when a human decides on the prompt. So, we're sitting in a room, we're drinking coffee, the sun's shining, and we're coming up with prompts. And then alternatively, when a language model is optimized in some kind of way, maybe similar to the way that I just showed you with assigning scores and then re-ranking them, but in some kind of way, also developing these prompts. So you have two different prompt alternatives. Which one wins? And they consistently find that the prompts that are optimized by language models actually perform better on mathematics tasks, which means that you solve more problems on a test set of mathematics problems if the language models are actually optimizing these specific prompts. So then the question is, what are some examples of these prompts? So I want to give you just two examples of the prompts that have been optimized by another language model system. So here's a prompt that was optimized for Llama 13 billion. So this is one of the language models. Please provide a step-by-step explanation of how you arrived at your solution to the prompt, including any necessary definitions or assumptions, and explicitly stating any loopholes or constraints. So, like a very seemingly simple prompt that that the language model kind of discovered through iterative refinement in some capacity. But now this is really interesting because for some more complicated models, such as Llama 70 billion, this automated prompt engineer discovered much more unique and creative prompts. So now I'm going to show you a prompt which performed the best on answering 50 mathematics tasks. So they tried out many different prompts, think step by step, do this, do that, and they tried this prompt as well, and this prompt performed the best. And the prompt is the following. Command, we need you to plot a course through this turbulence and locate the source of the anomaly. Use all available data and your expertise to guide us through this challenge situation. Then you also prepend captain's log start date, you insert the data, so that means your specific problem and task. And then you say, we have successfully plotted a course through the turbulence and are now approaching the source of the anomaly. So what's really interesting and like ridiculously funny in a way is that a language model optimized the prompt such that it mimics a Star Trek plot. And inserting information in the middle of this prompt turned out to perform extremely weirdly well on 50 math problems. But this prompt only worked best for a set of 50 math problems for a 100 problem test. And so for 100 problems, there was a different prompt that actually won, which was putting the AI in a political thriller. So the best prompt was something like this, that you have been hired by important higher-ups to solve this math problem. The life of a president's advisor hangs in the balance. You must now concentrate your brain at all costs and use all of your mathematical genius to solve this problem. And then you know the problem. And clearly, it would be quite unintuitive for humans to do it. And why it works is clearly still just an empirical observation. There's not a lot of theory supporting that. But this is just to give some information about what's happening under the hood. So to summarize question 3, can prompting be automated? The answer is yes. Automated prompting typically beats humans. This requires a language model to work both as a system that produces the answers, a system that scores the answers, a system that revises the prompts. And there's no really magic word, magic prompt. These prompts will differ from task to task. Many frameworks exist for automating these prompts, and different people currently use different frameworks as they're useful in different cases. Good. So now we know that prompting can be automated. I wanted to just very quickly give you the concrete frameworks that you can use immediately in your work. So what do I mean by automated frameworks? So it turns out that language model prompting can be abstracted away. So many frameworks currently exist. And what you can do is you can simply prompt everything yourself, but you can use a framework that abstracts away a lot of the prompting. This sounds really nice, that you don't need to prompt everything yourself and you abstract away, but it can be really, really dangerous if you start to prematurely abstract away, because I've seen in many cases people abstracting away simple tasks and then working a lot of time working within a Python library to actually get it running. So just consider that there are some drawbacks to using some sort of Python packages that abstract away prompting altogether. But in case you do want to do that, there are many such libraries. And so some of them include LangChain and Llama Index AI, GripTape, TinyLLM, BondAI, DSPY, Graphlet, Adaflow, LLMware, LLMflows, and a few more. So these are all libraries that try to abstract away the chaining of different items, the prompt construction, the prompt optimization, the retrieval part, such that you wouldn't need to physically write everything yourself. So maybe just giving you 2 quick minutes, an example of this one library that is becoming quite popular, which is called DSPY. And DSPY is a library developed by some people at Stanford, where they basically say, hey, look, if you want to build language model systems yourself, you need to write the prompt, you need to write the prompt that you need to break it down yourself. You need to then tweak the steps that everything would work somehow together. And what they do is they kind of try to say, can we, instead of writing everything in text and strings, abstract it away such that you're actually coding instead of writing prompts. And so this is an example of how you could use this library DSPY to actually program instead of prompt language models. So what you do is you would write a class, so just a simple Python class, where you have some sort of question, and you write that the question is dspy.input field. Then you have an answer, which is dspy.output field. So you're basically saying you have an input, which is a question, and you have an output, which is an answer. And then the task is generate a joke. And then you initiate this. You say, let's predict that this is a joke. You generate this joke. And then let's say we ask how to learn LLM prompting. And then this language model gives us a joke. Just keep prompting. It's like telling a joke. Sometimes it lands, sometimes it doesn't. So the idea is that instead of writing a full prompt and doing everything ourselves, we basically now converted this task into a programmable problem. And in this specific case, one thing we did is notice we wrote dspy.predict, but there's actually more sophistication here because you can suddenly start not using just predict, but something like chain of thought. So instead of writing dspy.predict, you could say dspy.chain of thought. And internally, it's going to go through a few different steps. It's going to say think step by step. Then you're going to get the thinking process. And then you're on the basis of the thinking process, you're going to get an answer. And then you're going to get the answer. And everything is done by simply swapping out one letter of predict to another word, which is chain of thought. And so you get a different answer. And so you could potentially inspect this answer, and you can see just a rationale, which is the think step-by-step part, and the answer. And so I think since I want to leave some time for the Q&A, I'm not going to finish up with the DSPY, but I think the main takeaway here is that there are libraries that can abstract the prompting away, and you can use them. And so I clearly prepared way too much for this, but this is only because I really care about this. So yeah. So let me just summarize this very quickly. We had 4 different questions we wanted to talk about. So one is, what is the current state of the art in LLM prompting? And so we said that there are 4 methods. So one is changing the prompt template, in-context learning, changing the thought generation process, and changing how many iterations you have. Then question 2 is, how are you using these in current systems? And so in practice, what happens is that you're building mostly AI agents. And AI agents is just a bunch of really diverse prompting. And these agents have different capabilities. So Sam will tell you all about it. He has done some really, really amazing work there. And so you have memory and tools and actions, and you have reasoning and thinking styles. And these different agents typically have slightly different implementations, but under the hood, it's some sort of prompting where you chain together outputs, you save some outputs, you input some, you then upload some inputs, etc. And how do you combine that into one broader system? Then can you automate prompting more generally? So yes, typically automated prompt systems are much better than the ones that just are human crafted. And you can also chain them together to introduce more complexity if that's what you want. And then there's the 4th one, what are some concrete frameworks that you could use? There are quite a lot of them. Many exist, try them out yourself. Abstracting prompting away can be very useful. It can also be dangerous. So make sure that you kind of check out different ones. And I gave you a brief example of one of these frameworks, the SPY, that attempts to replicate how you program instead of prompting. But I showed you some other ones that you can also look into. Yep, I think that's it. Thanks so much. And I'm wondering what's the typical question session. Maybe you can, Andreas, guide me a bit?
Yes, sure. Thank you very much, Paulius. You seem to have struck a very good tone. There's lots of praise for you in the chat, which is brilliant. And yeah, there are some questions. If you don't get through all the questions, as I said before, you can catch Paulius in the mentor session later for some more deep dive into this. The first question is from George. If you want to say your question.
Hey, can you hear me?
Yes.
Perfect. Paulius, thanks very much for the really great talk. My question was actually regarding the in-context learning, or actually the concept that you presented in order to kind of perform good in-context learning. And you mentioned that kind of certain patterns, like having, I don't know, right answers and then wrong answers, for example, isn't that good because of a certain pattern that the LLM could use, kind of. And then you presented that kind of an alternating order would be better, but isn't that also a pattern that the LLM could kind of pick up and could be guided by it?
Yeah, fantastic. Such a great comment. Thanks so much. Now I know that people are really paying close attention to this. Amazing. Yeah, so I think the most important thing is to simply not have a pattern. In this specific case, it's true that a random ordering where you randomly shuffle could be better, but it's probably better if you have, firstly, a lot of examples, or you're doing it in many cases. So, you're, for example, sampling 1,000 times, and then this randomness actually averages out. The problem with any specific one example is that, let's say you're giving 10 examples, and then in one of the cases, just by chance, you get that the first 5 examples are all positive, and then the first 5 examples are all negative, just by chance. And then, well, although this is random simply by chance, this clearly is for that specific prompt, not looking at the distribution of randomness, but just for that prompt. It introduces seemingly more of a pattern than just, let's say, flipping it or randomly shuffling it by like one the other. So I think here's like a bit of nuance into whether you're doing it once or are you doing it constantly. But I think typically, and you can play around with this, but just alternating it once or twice, I found it to be a bit more reliable than just putting everything and stacking it up. But yeah, you can definitely shuffle it. The problem, I would also just add one more thing of shuffling it all together, is because it might be a bit harder to replicate stuff. Because if you're, for example, doing 1,000 evaluation loops, and in every single example you're randomly shuffling stuff, you might really, have this benefit of shuffling stuff, but then you're suffering into replicability because it becomes harder and harder to actually get each output exactly right, because you're introducing more variability within each input. So there are trade-offs. I don't think there's really one good solution, but I think use your good judgment, and that's the best thing you can do.
Thank you, Paulius. I
Oh.
read one out because probably she wouldn't be able to ask them later in the session. Do you have a simple example task where the current SOTA models, such as GPT-4, would still benefit significantly from, for example, chain of thought prompting? Because I think most of these positive-negative classification tasks work pretty well from prior knowledge, and newer models seem to use step-by-step reasoning automatically for math problems.
Yeah, absolutely. So I think almost in all problems where there's more ambiguity and where you need to develop some sort of hypotheses on what's going on, for example, you remember the automated prompt engineer, it was producing hypotheses about what is the pattern. And I think in those specific cases, it's simply much better to have some more reasoning along the way. So I have 2 papers that are in progress, but both of them substantially benefited from having about 3 to 4 self-reflection loops, and each self-reflection loop is substantially helped by just thinking about what it is. So I think, yeah, definitely in very simple tasks, if it's a very trivial one, awesome. I think when you introduce more complexity in larger systems, that's when it becomes more important. So it's a bit of a generic answer. I know I didn't give like a concrete list of 20 different concrete examples. But I think maybe just as a proxy, the harder the problem, the more this is important. It should be a good proxy.
Excellent. Maybe one more short questions from Isla, if you want to ask your questions. Or I will read that one.
Yes, hello.
Oh, perfect.
Thank you. Do the size of the input matters? Like there is an ideal size of the input, because sometimes I feel that when we give a lot of examples or a very long input, sometimes some LLMs get a little bit confused. This is my personal feeling. So generally, do you have that sense of how much long the input should be?
Yeah, thanks for the question, Ayla. I'll be very honest in that this is a somewhat complicated question for a number of reasons, but mostly because it really depends on the task and what's in the input and what's the type of the model and what your goal is. And there's some research, quite a lot, showing that as you increase how much information you're giving, then the value of any point or any source of information decreases. But then, is each point of information important? Is it not important? It's really hard to say because there's no real science behind it. Most of these are just empirical observations. So in many cases, the best thing you can do is just to run some simulations and some experiments yourself and see what works, especially because this might differ from language model to language model. So what I say now might be not applicable for the next generation of language models. And this is because everything is just so experimental.
Okay, perfect. Thank you very much, Paulius. Again, as I said, if you want to catch him for a bit more, you can join us for the mentor session at 5:30. Thank you again, Paulius, and see you later.
Yeah, thank you. Thank you. And I'm jealous for all of you that you're getting Sam now. So enjoy.
High praise there. So I will hand over quickly to Nabil, who will introduce you to our last speaker of the day. Again, going back to large language models. So over to you, Nabil.
Yeah, so hi everyone again. So I'm pleased to introduce Sam. I think he's an amazing speaker to be our last speaker of the day. So just to give you a bit of background about Sam, so he's currently a PhD student in the Van der Schaar lab. He holds a master's degree in engineering from the University of Oxford with first class and with many awards. He's also got a bachelor's from the University of Oxford, and Sam has also worked in numerous startups doing very amazing things. Sam also has two very important things that I'd like to mention before letting him jump in. He's done some insanely impressive work on LLMs for coding, hence he's the perfect person to be speaking about this. But Sam is also a very accomplished researcher in time series and control. So I definitely recommend reading his works on neural Laplace for time series and control, if that's of interest to you, because that's been some amazing revolutionary work there as well. But I'll hand over to you, Sam, on LLMs for coding.
Thank you so much. Can everyone hear me and see my screen?
Yes. Perfect.
Yes, amazing. It's a pleasure to be here, and yeah, really excited, and yeah, very excited. I think the world is very exciting, and how you can use LMs specifically for code generation, and what new exciting possibilities this opens up, which we'll go into in this presentation. But if anyone has any questions, just unmute the microphone and ask them directly. It's a bit hard for me to see the chat, so yeah, if anyone, that'd be great. Cool, great. Okay, let's get into it. Okay, so a quick agenda. And also, if anyone wants to take a few-minute break, I'm just going to do a quick intro to begin with, and then I'll go into history of AI for code generation, and then benchmarking code generation performance, and then we'll specifically look at applications and agents. Specifically, we'll look at one of the papers I've done, and then I'll also talk about 3 preprints which are currently under review, and also future work, which I'm very excited, and also tools that we can use today to actually improve what we can do with generating code with LLMs, and what new possibilities this opens up, and how we can actually design new things like algorithms or even new frameworks around this. So yeah, Nabil was very kind to introduce me. I'll have a very quick introduction. I'm currently going to my 4th year now, mentored with the amazing Mihaela van der Schaar. And at the moment, I actually have 4 LLM code generation papers. 1 published in iClear this year, which I'll be talking about in this talk later on, after I give a tutorial about LLM code generation, and also 3 under review. So that's kind of news pending, which I'll talk about at the end. And my main interest is actually being in model-based RL, specifically looking at continuous time modeling for RL and RL for discovery, which I can expand if there's interest. And to date, I actually published 6 first-level papers in top-tier conferences such as NeurIPS, ICML, iClear, and AI Stats. And fortunately, I've been recognized by the community with a long RL top 2% of papers in ICML 2022, and also Spotlight as well in iClear this year. Great. So brief history. So what is code? What is generating, and why are we here? So really, there's been a whole line of work, mainly starting from the pre-LLM era, where we could actually train recurrent neural networks, a form of recurrent neural network model, on generating code, such as this code neural network from 2016, and it could also summarize code as well. Then we got into kind of early applications, so the kind of GPT era, which stands for generative pre-trained model, in this case Codex, or GPT-3, GitHub Copilot. And we can actually get into really good applications of now actually using LLMs as kind of AI assistants, if you will, now use GPT-4 or even open source LLMs, which are quite capable of code generating. So you can see the kind of generation as it's gone on here. And you can even try a quick demo, which is a code to sequence for AI, better code generation and summarization. So what's kind of the most useful tool that you may have come across? I'd recommend anyone in academia to sign up to GitHub Copilot. You should get a free subscription if you use an academic email address. And this really is a form of an LLM that will actually kind of predict, like predictive text, but for predictive coding. And actually it's been shown, somewhat empirically, to actually speed up developer performance. So take your existing code writing skills and you can potentially write code using such a tool maybe 20 to 30% faster. Now this is really useful. So we'll go into how some of these tools work, how they're trained. And also, I suppose, yeah, you might be familiar with GPT-4 or ChatGPT. You can obviously ask it for really any most popular code language problems these days, and it will respond with something reasonable, although it may be overconfident and may give you syntactical errors as well. So, what are some of the applications that may be actually around today that you really leverage in LLM for code generation? So one of the ones which we'll talk about in detail is L2Mac, which we'll go into later, and there's also a few other competitors on the slide as well. So how do we benchmark code generation? So of course we can ask an LLM to generate code, but there's a very famous data set called Human Eval, and actually you can see one of my papers is benchmarked on the benchmark. They're highlighted is L2Mac, and Human Eval is a data set of essentially 164 human-designed kind of low-level or junior software engineering problems that you might encounter in an interview. And the LM is tasked with getting a prompt and getting a function description and actually having to complete the algorithm, which will then be tested on some held out test unit cases, which are then evaluated. And this pass at one accuracy is how many, the percentage of those programs within the 164 set, what the number of passing essentially programs compared to the failing programs. So a perfect score would be 100% here, and a low score would be maybe 25%. Some of the early work here, and you can really see actually we've really seen a revolution in the past really year. Actually, really I suppose the ImageNet moment of code generation tackling some of these problems, which I think is really exciting, and we're actually going to see more and more work. You may be familiar with some of the work like Automated AI Scientist, which is coming from Scana AI. So, okay, let's go into it. So how do we measure this? So, for instance, a human eval problem like Shen et al. 2021 is the most widely recognized research benchmark for code generation. Now, this paper introduced Codex. It was by OpenAI, and the first major code-specific LLM. And again, yeah, it's 164 human handwritten programming problems, each with several unit tests. And you can see an example here where we get a description, in this case, return a list with elements incremented by 1, and the user would, in this case, the LLM, would have to actually write some code. So this one's quite simple. You should be able to get this right. Now, the prompt is provided with the black background, as you can see. The successful model generation completion is with a blue background, and it has to pass unit test to be successful. So there've been multiple extensions to Human Eval. It's really actually quite overfitted these days in terms of data sets and benchmark. So there's different variations or flavors of it, and also extensions. So multiple E is a data set of evaluating large language models for code generation that supports 18 programming languages and translates Human Eval problems into other languages. Human Eval X consists of 820 high quality human crafted data samples paired with Human Eval's 164. And the most basic Python problems is the data set of 1,000 crowdsource Python programming problems. We also see companies create their internal data sets on which they evaluate. So Google obviously has Gemini, and they have a benchmark called Natural to Code, which is public. And also GPT-4 has slightly better on Human Eval, and also Gemini as well, Natural to Code. And Meta has also released unit tests for its internal LMs as well. Now, why held out non-published benchmarks valuable? So AlphaCode by DeepMind created a code contest, a data set compiled of competitive programming problems. And increasingly, data sets from real-world tasks for humans are needed as models approach human-level performance. And actually, a lot of the, I suppose you can argue, maybe potentially human-eval problems could be included in some training data sets. It's unclear whether they are or not. And also, as we see more code generation problems, new data sets are a really good indicator of the performance. Like there's a really famous one called SweBench, which still is largely unsolved, but is actually in the past, I suppose, 6 months being increasingly solved, which is exciting. So we can see some data set problems solved here. And in this case, this is relating to code forces competition. And we're still nearly at the point where we're trying to be better than maybe a human competitor. Actually, going back to the human eval problems, they're really like junior entry programming problems. And we still can't, I suppose, reliably 100% on that. But also it could be some of the, a bit like ImageNet, it's very difficult to get 100% because there's mislabeled problems. And I believe there's a few mislabeled problems in human eval, at least incorrectly specified, that would make a language model really struggle on getting them. So, what's some of the real world impact we can do with such a great LM code generation problem now? So as models begin to surpass human performance, they will obviously be measured on impact. So quite exciting, AlphaDev discovered a faster sorting algorithm for small lists that is now being implemented in the C++ standard library. And also software engineering KPIs, such as bug rate PRs, are starting to become more commonplace. And we're actually really seeing this more. And actually, I really encourage you, towards the end of the talk, we'll look at actually how you can use some of these very powerful tools to actually discover new algorithms, which is, I think, very exciting. And we'll talk about why that's possible today. So benchmarking code generation, let's start with maybe looking into human eval. And we'll go from base models, and then we'll go to fine tuning, instruction tuning, and then we'll go to techniques on how to improve a base LLM in an LLM agnostic framework like L2Mac or other variations. So base models are the ChatGPT or the GPTs of the world or llamas of the world. And really, they're not fine-tuned for a particular task. And really, we have open LLMs where the weights are open, easy to customize, and we can download them and run them and really play with them. We can easily fine-tune them. And we also have closed source LLMs, which obviously limited to just doing API calls, but are very capable models. And really, those excel at code generation quite well. So if we look at some of the code generation models benchmark in terms of parameter size to pass at one score in human eval, we can see actually there's quite a few comparable, well, and good open source models. And we can compare them against the actual, if we instruct fine-tune these models, they become better. This case for code, as we can see in this graph, compared to the previous one, as expected, as with most tasks for LLMs. Now, instruct-tune models that are fine-tuned with instructions, in this case for code, really it involves a prompt which contains an instruction and a response. Following the instruction is important for the model to know how to understand the new instructions at inference time. And really, actually, it's quite dependent on the format, and really you're training it to this particular format. In this case, we'll have a model input and a target output. In this case, synthesis, which is actually from Octobench, a coding generation benchmark. And they looked at also fixing bugs as well. So I believe these were generated from the human eval data set. They obviously, this human eval is the same synthesis task, and then they modified it, extended it to introduce code bugs to determine if an LLM and train an LLM to fix code bugs in this case, and also explain code to really help explaining kind of terse snippets of code in this case. And then instruct tuning is clearly useful. So how can we use it? So LLMs and data sets get larger. We increasingly need to think creatively of how to gather data in order to improve. And one example of this is CommitBack, which is 4 terabytes of Git commits across 350 programming languages, and also comes from this paper called Octocoder. And Git commits naturally pair code changes with human instructions. And we're actually seeing Git commit datasets become more commonplace as code generation capabilities become stronger, particularly for SweBench, or stands for software engineering-based tasks, as we'll see more of that. So technique can make all the difference. So this is really broken down into reasoning methods you may come across or seen in presentations already today, and decision-making methods. And what's really interesting inside is we can actually generate essentially a higher score in human eval by just using better prompting techniques, which we'll go into, compared to a base model of GPT-4. So the benchmarking code generation. So you may be familiar with chain of thought. So this naturally improves really a general purpose prompting method and prompts the LLM to sequentially generate reasoning steps from an input to output. And this was first introduced in Palm and SCAME language modeling with pathways. However, it suffers from error propagation, particularly for code, as the chain length increases. So there was future work on Trigger Thoughts, which is kind of a graph-based search algorithm, and they explored breadth first search and depth first search, and it actually explores multiple reasoning paths by using search algorithms. In this case, yeah, breadth first search and depth first search. That said, it's limited by relying solely on the LM's internal knowledge. Now, a few further work onto this is reasoning via planning, which uses Monte Carlo tree search for planning chains and reasoning. However, it again lacks external feedback. And external feedback in this case is really interesting because for code generation, we actually have many valid external feedbacks. Most importantly, just semantically, is the code valid? Could it compile? And then actually, if we have some sort of performance metric, we can derive out of that. We can then actually get some sort of performance metric or reward metric, which we can then actually use to improve as we search through this planning-based approach. There's further decision-making methods, in this case, REACT, which stands for Reason and Act, and really prompts the LM with alternating actions and observations for decision-making interactive environments. And there's feature works which actually build on this, like reflection, which go into, and however it can greedily follows one trajectory and really can't adapt. And reflection in this case adds self-reflection to REACT. This improves overall performance by allowing the LM more time to think through the problem, similar to chain of thought, and actually works by storing a buffer of previous lessons from previous episodes to improve the rollouts in the future. However, it does really consider alternative options at each step. Now, one of the existing state-of-the-art methods for just single-shot code generation is language agent tree search. In this case, it's called LATS, and LATS unifies the strengths of both reasoning and decision-making methods through principled search while overcoming limitations via environmental feedback and self-reflection. GPT-4 plus LATS is the current best performer in human eval benchmark with a score of 94.4. This is actually somewhat incorrect now. I believe the benchmark has been updated, but it was state-of-the-art for a while. So there's a famous quote by Jensen Huang, the NVIDIA CEO, who says, "Software is eating the world, but AI is going to eat software," which I think is quite exciting. So let's go to how we can actually use some of this. So AI has really tackled every aspect in software engineering today, and we see some of the, so if we look at, I suppose, tools or frameworks, in this case, a lot of them products, and the top one on the left is actually a paper, L2Mac, which is a LLM code generation framework. You can give it a single prompt, in this case, L2Mac, and it can generate you an entire code-based repository with working files that implement really what you want. And then we also see things like migrating code from one language to the other, interactive developer environments, where you can, again, a bit like Copilot, where you can help rewrite code faster. You can also document, essentially create auto documentation and tests for code, and also, again, document code as well. So let's take I'll just take a quick look at any questions if anyone has any. Let's see. Okay, yeah, feel free to unmute yourself and ask any questions. Yeah, okay, yeah, I'll go a bit slower. Thank you, everyone. Yeah, do give more feedback. That's really useful. Okay, so we're going to actually, yeah. So this was a paper in iClear this year called L2Mac Large Language Model Automatic Computer for Extensive Code Generation, and this is work by myself, my amazing author Max, and my very good on the supervision of Mihaela van der Fischer. You can find more information about this particular paper on my personal website you see below. So let's go into actually just recap from the beginning. So transformer-based LLMs are constrained really by their fixed context window. You may have seen already, and how they work really is mainly a decoder. In this case, generative pre-trained decoder, which is like GPT-3 and potentially GPT-4. And it works by putting a sequence. In this case, you can see the sequence in and sequence out, and it autoregressively fills in the next token in this case. And in this case, we're doing this for code generation. But actually, you can see in the bottom actually we normally have a limited context window. So I believe GPT-3 originally had a context window of 1024 tokens, and actually GPT, as they get larger, we see increase in context window. But this work particularly looked at about a year and a half ago, what happens, how can you generate very large amounts of code with a very limited fixed context window LM? Of course, this is not really the case these days, but this is where the world was about a year and a half ago. So LMs really excel at general text generation tasks within the context window limit, but how do we actually get them to generate larger code bases, which is really what we want to do. So in this case, so how LMs really critically struggle when generating large outputs, larger than their context window, such as large code bases that are both extensive and internally consistent due to the information loss and contextual truncation imposed by the finite context window. So in this case, we see a human eval actual prompt, in this case, write a Python program for a given list of integers, and normally the LM can respond with a pretty good response actually in the context window. But how could you get an LM to actually say generate an entire large code base of many thousands of lines of code? This problem hadn't been tackled before this paper in like academic setting. So we looked specifically at this and how you could approach it and improve just using an LLM in this case. So how could you actually generate a lot of code which is significantly larger than the context window constraint? And this is what we can do. So you can take a requirements file or a single prompt, give it to a LLM framework, in this case L2MAC, which is a memory-based retrieval LLM framework, and it can generate large amounts of output. Also, actually, we'll show at the end, it can also generate entire books from a single prompt, which is quite nice. So really, limitations of existing memory-augmented LLM methods. So current memory augmented LLM approaches cannot really handle extensive generation tasks since they, one, only focus on reading memory and reduce its evolution to concatenation of new memories. So we see this in works like Reflection, where they just use a memory buffer and append lessons to it. And this really makes errors irreversible and prevents adapting previously generated outputs as the task progresses. Or two, using specialized memories, such as databases, to maintain precise values for variables, such as dictionaries or databases, that cannot adapt to other domains, such as code. Now, really compounding these shortcomings, memory-augmented LLMs do not include mechanisms for maintaining syntactic or semantic consistency within the external memory, a vital requirement for the generation of coherent and independent extensive outputs, such as the generation of an entire code base. And what we mean by this is, you may be familiar with a code base, say in Python, you can import multiple files in different import structures. So it's very, I suppose, multiple files depending on each other files. So it's not exactly too clear how the structure relates to each other as you're building up this code base. So we introduced this LM automatic computer framework called L2MAC, which is, we like to say, the first practical LM-based general purpose stored program automatic computer, which is a von Neumann architecture framework, which you may be familiar with from maybe electrical engineering of how to load memory between a CPU and registers. And it's an LM-based multi-agent system for long and consistent output generation. Its memory consists of two components, the instruction registry, which is populated with a prompt program to solve a user-given task, and a file store, which will contain the final and intermediate outputs. Each instruction in turn is executed by a separate LLM agent whose context is managed by a control unit capable of precise memory reading and writing to ensure effective interaction with the entire file store. So in this case, it uses a Unix file store, so it can write as many files and is the same hierarchies as maybe just the existing file store on a Unix machine. Now, this gives a few immediate benefits. So we get strong empirical performance. So obviously, this is quite dated now, I realize, but we do get good state-of-the-art performance for large code-based generation tasks, and we achieved good performance on human eval as well. And unfortunately, it's not third in the world anymore, but it was on the previous leaderboard if you go back in time. And we can generate near unbounded length outputs, significantly bypassing the finite context window token limit, and we can produce detailed outputs that fulfill complex user-specified requirements. We can also automatically error correct generate outputs, such as code that has syntactic and functional errors, and we can correctly condition on and integrate with existing previously generated outputs. I'll just check for any more questions, but you do let me know. Actually, yeah, Nabil, let me know if there's any questions. Actually, yeah, there's some questions. Yep, great. Very good. Okay, so So I'll go into a bit of a figure to show how this is done and what's going on here. So we'll walk through a nice animation, and yeah, I encourage questions. So a user could come along and with a single prompt and say they want an entire code base which allows a chat app which has sign up, web version, or privacy settings or admin roles. The LLM can then break this down into a set of sequential instructions. In this case, kind of steps, very similar to a prompt program inside a computer, hence the von Neumann architecture. So in this case, set up a structure, create registration, create profiles, and create web interface. Of course, this is a simplified toy example. I encourage you to check out the paper or check out the website for more detailed actual discussion of how this exactly works. But each instruction will then be loaded into a separate LLM, which has a fresh, clean context window. And this is actually managed by a control unit, very similar to a computer architecture, which the control unit will give the initial instruction and actually tell the LLM that it has access to some tools to write code out to a Unix file store and also read code from Unix file store. In the beginning, the file store is actually empty. Now, the LM can actually respond with calling a particular tool to write some files out in Tamden. In this case, it writes initial app class. It looks like it's using Flask, and also it writes some unit tests as well. We specifically instruct it to write unit tests. And these are really useful because once it writes code, we, inside the control unit, actually check the code for semantic correctness. So if it made any typos or anything, we iterate the error with the LM to correct that. And also we run all unit tests. This is really useful actually, as we'll show, because this actually checks that some of the functionality that was designed to do is implemented correctly. Specifically, when we actually modify files, we can run unit tests to check the previous functionality, which should be working and implemented as before, doesn't break. And if it does, we can fix it. So in this case, the code is valid. The control unit gives a message back to LM, and then it asks the LM actually, have you actually completed this instruction? Now, this is quite common because actually agentic frameworks such as AutoGPT or AutoGPT in some case, it takes a prompt and then it creates 5 high-level goals, and it just kind of executes those goals, and it can update it itself, and actually can kind of get confused because it can kind of just go down things that it wants to do. Maybe it's just continually researching, or yeah. So, but in this case, where we actually ask it, has it completed the task? Because sometimes the LM may just discuss the task rather than completing it, and maybe the actual step actually might have more detailed instructions. Might be set up the structure and run some unit tests and verify they're working. And it can actually look at the initial instruction, check that it's completed all those initial things in the initial instruction, and then if it has, it can then say yes, it's complete. At which point, then this gives us a summarization step, what's happened within this context window. And in this case, it gives a summary of the core application that's been set up. See, there's a question, great. Yes, yeah, prompt time, yeah, potentially. So, the summary will then be fed along with the second instruction, in this case, create a registration, and the summary into the next control unit. In this case, and the LM actually in this now has knowledge of which files, just the file names at the moment, or which file names exist within the file store. And just given this limited information about the file name paths, it can then actually use the tool to actually read the file within its context. So it realizes it actually needs to read the file app.py. So it reads this into the context window. And then by having this, it can correctly condition on app.py to overwrite app.py to actually add additional functionality. So in this case, taking the initial application setup structure and adding, in this case, registration. Yeah, so that's a great question. So Ivan, thank you for asking. So was there any change in performance in multi-program language required? In this work, I only evaluated it in Python. Potentially it could be implemented in Python backend. Yeah, I mean, actually you can, I mean, I have seen it write JavaScript code for the front end. It does that naturally without me really specifying it. You can definitely set up more languages. I encourage contributions for that. There probably are frameworks to do this already, because this work was a little bit, well, I mean, I suppose it came out this year, but really what you need to do this in any language, if I just go high level, you need some sort of way to verify the code is semantically correct. In this case, in Python, you can just pass the code through a Python static analyzer. And in this case, you can say it's valid, and also a way to run the unit tests. And if you have that, you can then really support any programming language. And you just need to create tools for the LM to semantically verify the code and also run the unit tests, and then iterate the errors back. So if you implement those two core things, that should be possible. So there's another question here. Does the unbounded limit of L2MAC affect the quality of the output in any way? Yeah, I mean, that's a really good question. Are there any downsides to increase the limit in the output, perhaps? So yeah, the unbounded output limit in L2MAC, it can, obviously, yeah. So if we, in this case, created many instruction steps, and I think I do in the appendix up to like 50 or 100, it can get actually stuck sometimes with errors or creating things which are incorrect. So actually I encourage people to build on top of this to kind of, you're kind of dependent on the initial instructions, very much like a program is dependent on its program that's written for it and it's executed. If the program's wrong, then obviously the program executing will fail. And in this case, if the instructions are somewhat wrong or very wrong, in this case, maybe there's 50 instructions and step 58, 38 is incorrect, then it will kind of get stuck and will really struggle. It's actually, yeah, I encourage future work to build on this to actually iterate and actually improve the instructions. But in the initial case, up to about 5 to 20 instructions are normally quite okay. Okay, so I'll just continue here just so we keep the flow. So if there's an error in this case, it's updated some of the functionality, but it's broken some of the functionality before in the file store, then obviously the code is checked for the unit tests, and actually, oh no, it's failing 2 unit tests. So the error will then be propagated back to the LM, and the LM has to actually fix the code into a complete working 100% passing state for it then to actually get the valid code for the file store, and then it will actually repeat the same steps of summarizing and then giving it to the next instruction. And this will continue until all the instructions are executed and completed. And at which point, at the end, you'll get a nice, essentially a file store or a code base of your entire code, which is quite nice and actually provides a nice starting point if you wanted to do something. And in this case, actually, I think someone commented, it's actually written out HTML files as well, which is quite exciting, although it wasn't specifically prompted to do that. So yeah, we see, I suppose, a broad framework here. So now let's go into actually how this works. So really it forms a control unit, much like a computer control unit. And I know there's many symbols here, but we'll try and go through it. So really we start with a context window, which is a series of messages, which is fed into the LLM. And the LLM then processes this, essentially an API call, and then we'll respond with the message. Now the message, actually the LLM is also instructed, it has access to tools. It can sometimes invoke a tool. If it does, it can read, write, or evaluate the memory store. So evaluate here means checking the code is semantically correct, and also running unit tests, and essentially getting a Boolean of whether it passed, and then if it failed, the string response of the failure cases. And then if that's correct, the control unit will then actually essentially check whether the LM is called the completed step. And if it has, then it will actually check the memory to all unit test passing. If that passes well, then it will summarize, clear essentially the context window, and then load the next instruction. But if some of the steps are incorrect, maybe it's still continuing, it will then actually append a cycle message. And this cycle message is quite key. And this really says, continue looking or continue executing the current instruction and respond, essentially, tell me when you've completed it. And if not, just continue implementing or doing that task. Maybe that's generating unit tests or completing this, and it will continue iterating that. And this is the normal control flow. But sometimes actually, specifically in context limited with LLMs, you may actually exceed the context window. Now, what happens here? This is an interesting problem because we still want it to continue the instruction, say create a registration page, but it's run out of context, so it can't continue. So what we do is we unwind the oldest messages, we summarize the current progress, and then we clear the context window, and then we give the next summary with the same instruction and repeat the step. And this is quite key because we've seen it actually do behavior like had to scan a code base to find a file, and it wasn't particularly clear where the file was or bad naming structure. So it actually had to scan multiple files, then it ran out of context. They could summarize put that into a message, and then give it to the next instruction, and then it could start with a better informed way of where it should start. Now, output checks are really key to correcting generated outputs. For example, code that has syntactic static errors or functional errors, say unit tests that are failing, whilst conditioning on and integrating with existing code base in the file store. Now, if we look at related work, so this is the first work to, or first method to produce detailed user-directed extensive outputs beyond the context window limit, token limit. In this case, we can do things like we can handle context correctly, compared with, I suppose, AutoGPT or single LLMs or even reflecting LLMs like reflection. We can precisely read and write the entire memory at any point, which is quite nice. AutoGPT, in theory, can do this, but it struggles. So I'll go into some of the corner cases there. And also, we can check generated output as well. And yeah, so AutoGPT, such as autonomous agent LLMs with memory, immediately summarize the user input into a few sentences or goals and consistently summarize their past actions when following these goals. And this is how they get around the context window constraint limit, leading to forgetting exactly which files they previously created in the past and a loss of user-specified required information to implement. Now, we'll go into this in a bit, exactly what happens. So, we created our own benchmark in this case for large code base generation. And we see that actually we can implement the highest number of functional features specified that are fully implemented and the number of syntactical errors in generated code and the number of lines of code as well. What we see is we can implement the highest number of features compared to existing benchmarks or baselines with a few errors, quite good lines of code, and also the highest number of tests passing, which is self-generated, which isn't a very good evaluation metric to use. And which was quite nice. Really, yeah, we get minimal syntactical errors and high pass memory unit tests. And therefore, it was state-of-the-art for completing these system design tasks of large duration benchmark tasks. Now, how did it compare on human eval? So it actually was, when we benchmarked it at the time, I think 3rd or 4th in the world. Of course, this is now saturated. So this is old news, if you will, about a year and a bit ago. But yeah, so that's good. So there's a question here: if the code suffers failed unit tests, in the case it is because the test is wrong, how can we be sure it does not break the correct code to pass? Yeah, so that's a great question. What to do when the unit test is incorrect? Now, we actually instruct the LLM if it continually is trying to fix the unit test and the unit test is wrong, to actually also inspect the unit test and actually modify the unit test if it's incorrect. Because really the tests are there to help it kind of build code, not to be a deterministic source of truth of that's true or that's false. It's more kind of scaffolding or guidelines to help it check its previous iterations. So we actually do assume that the tests can be wrong, which is a good assumption. But that's a common problem in code generation problems, specifically generating language agent tree search. LATS has the same problem, and it's really difficult to determine something that's generated whether it's true or not, given you really only have access to the generator. You'd need some sort of external input there or validation. Yeah, so we'll just go into this, and then I'll take questions probably at the end. But do keep them running, and I'll be sure to get to them. So we also performed some insight experiments. So can L2MAC correctly perform task-oriented context management? And this is essentially not removing stuff from the context. So practically, it can actually observe code L2MAC and retain a high number of user-specified feature requirements within its instructions and perform instruction-oriented long-running tasks. In this case, actually, AutoGPT, as I was saying, if you give it a detailed prompt, it will summarize the prompt into 6 short sentences or high-level goals, whereas actually L2MAC can actually save a lot of the detailed prompt requirements into detailed instructions, and that really helps it by not forgetting what was asked the user to do. We can also look at how it can perform precise read-write operations to the entire file store. So in this case, L2MAC has an understanding of the existing code generated that allows it to update existing code files, even those originally created many instruction steps ago, and can view files when it is not certain and update the files throughout writing the files. So in this case, we see a color histogram of essentially dark means files not created, white is files exist, red is the file written to, and blue is the file read from. So code L2MAC in So we have on the Y is just the number of the index of the files. And it could obviously say the first file created is, in this case, well, shoot file index 10 and then file index 0. But it can continually read files that's created a long time ago and then continually update them as it updates different features and implements new features within the code base. Whereas AutoGPT suffers from a problem where, due to its truncated context window limitation, it creates files and then a few instructions later, it forgets that it even created this file. So it will actually potentially create the same file again, or actually reimplement things, and yeah, it just leaves an awful mess really, as it wasn't really designed for this. So we can also correct the generated output and error correct. So whenever errors do arise, of course, LLMs do hallucinate, they do produce errors, they are a probabilistic generative model for text output. So we expect errors actually, and they can easily detect this error by using the external validation of running the semantic checks on the code and also running unit tests. And when errors do arise, we can iterate in the system to fix them. And yeah, that's quite novel. Well, I mean, there's been other work doing this automated code correction previously, but it works in this case quite well. In this case, errors are generated, unfortunately, and then they're corrected. Whereas, say, like AutoGPT, errors will be generated, and then it forgets it created that file, so it will struggle to fix some of the errors that it's created previously. So what are the contributions? So in this work, we contributed the first practical LLM-based general-purpose stored program automatic computer, von Neumann architecture framework, and LLM multi-agent system for long, consistent output generation. I know that's a long sentence, but it really uses checks, such as code checks, to correct generated code that has syntactic and functional errors within whilst conditioning on and integrating with an existing code base. And L2MAC can generate large code bases to solve for the first time high-level system design tasks of creating entire applications. And we observed that it was state-of-the-art. I'm not sure what it is today. And now it enables a practical tool for large output generation, such as code bases or entire books. And we can execute long-running large output tasks with an LM as an AI system, which is quite nice. There's a particular dedicated website here you can go to, Sam Holt, github.io L2MAC. Has some good documentation and a GitHub as well. I'll be honest, the GitHub has some bugs due to the OpenAI's functional implementation update, but the fix should be coming soon. But if you use an old version of the API, back in April this year, it was working. But you can pip install it with this, and then if you configure the LM credentials to your LM preferred source from OpenAI, you can then give it a prompt like create a beautiful, playable, simple snake game with Pygame, make the snake and food be aligned to the same 10 pixel grid. And what this will produce, it will produce 3 files in your local directory, and then you can actually just run this, and it's a playable game, which is quite nice. You can also do the same for more complex things, like create an entire, well, in this case, a URL shortener web application, the example we used from the paper. And actually, you can see the LM actually outputs files such as JavaScript and CSS and HTML and makes them work together. In this case, it provides a URL shortener mini application, which seems to work and actually tested. I believe the code should be potentially in the paper, if not in the GitHub repo. We can also use it to do things which it wasn't really designed to do, like generate an entire book from a single prompt. So in this case, I believe it was generated an Italian pasta cooking book, and it generated an entire book complete with table of contents, chapters, individual chapters on particular topics, and then summaries at the end as well. And then actually this image was AI generated, but yeah, that was just for fun. So you can see something like this. Really, the text is what we're looking at here, which is the output of the method. It marked down. So you can see more of the paper here and the website here. I'll just jump to questions now, but I'll stop for questions at the very end too. Okay, yeah. L2 computers evolved naturally. Wolf, I'm not sure I fully understand, but I'll try and answer it. If L2MAC style LM computers evolved to natural language machine code extremes, how do we ensure human comprehension and control of critical systems? Oh, right. Yeah, that's a great question. I suppose you have to kind of get an expert to interpret them. And actually, I'll go into, I mean, that goes into future work that I've have some preprints pending. Maybe I just answered. So what kind of stuff can you do now with LLM? I think LLM's code generation is extremely exciting because it's a very powerful kind of module you can use to do things. So you can use it to actually generate new algorithms for particular cases. So if there's an important thing that we care about as a community or individual, you can actually use the LM to generate code for that, and then actually feed this in an iterative loop and perform in-context learning to generate a better code for that. So for example, actually, I have a preprint for essentially giving new RLHF or offline preference organizations to fine-tune large language models, and this was discovered through code generation with an LLM in a loop, generating the code for the loss objective function, and then training the algorithm with that, and then giving the feedback to the LLM, and the LLM can actually, in context, give better and better code snippets to actually discover better algorithms for you. I think that's really exciting. And then obviously it's up to us as people to then actually kind of analyze what the code has been generated and actually determine whether it's realistic, feasible, and interpretable and actually useful. Because it could obviously, just like fitting maybe a neural network to a problem, or even some sort of regression, logistic regression-based task, you need to make sure that it makes sense. And it's just not overfitting to noise, I suppose. And you can kind of do this through standard machine learning tasks, so actually testing out and held out the validation tasks that you haven't actually trained it on. So you can do this for algorithm discovery, but you can also use it for neural architecture search as well. And actually, LLM is really a nice discovery method now, in this case, for something that was maybe computationally infeasible previously, like searching for an optimal algorithm with, say, before LLMs, people would use it into things like genetic programming, and that was really computationally feasible by representing maybe each text, character, or token as a mutable operator. Whereas an LLM, it has good understanding of how to generate code, in this case, and token synthesis into some sort of comprehensible code to actually allow it to search that space more effectively. But yeah, that's a great question. That obviously we as people have to check the code that's generated. Okay, more questions. Any code shall work in production? Yeah, I'm not sure what the question is from Divinash. Any code shall work in production environment at the end, but probably not. I mean, I would recommend to check the code. The code may get some additional bugs that weren't tested. I mean, of course, the code is only as good as the tests that are written for it. And it may not have implemented what you wanted either. So yeah, so I would always recommend having some sort of human verification step check at the end. Another question by Thomas: is it possible to write another software as starting base, providing L2Mac to create a L2Mac 2.0? Yes, I mean that we did this in the paper and the appendix to do exactly that. And yes, you can. The GitHub repo kind of unofficially has this implemented. You just need to give it essentially an existing dictionary file store, where the file store, in this case, it's a Python dictionary, and the keys are the Unix file names, path names, and then the values are just the essentially the text concatenation of all the lines of that file, and that should work. There's probably some examples of that, but write to me at the end, and I can add that, or open a GitHub issue, and I'll add that feature in time. Thank you, Division. Yeah, slides can be shared. Yeah, I think there'll be a way to do that. The version L2Mac. So there really is the API version from OpenAI. I believe it's been updated since I originally coded the implementation. It should work with the previous API version. I think it should work out of the box potentially. I haven't tested it for a couple of months, but I think with GPT 4.0, it probably doesn't work because they probably updated the API for GPT 4.0. GPT 4.0 wasn't around when this was written. So yeah. So yeah, I think LLMs for code generation is a very exciting use and tool, as we can see now. And give a bit more flavor of what you can do now. So you can actually use LLMs to generate code and then have them iteratively generate new code snippets and leverage LLMs' strong ability to perform in-context learning. So there's a paper from, in this case, Mini-Shot in context learning from this year, which shows that just by increasing the number of code samples, say in this case, I don't know, let's think of a tried example, create a sorting algorithm that's linear complexity to reverse sort or something like that. and then the LM would generate some sort of example. You could verify it, time it maybe bigger, or even just time it with Python, and work out the time and space complexity and give it back to the LM, and then repeat this a number of times. In this case, it's called shots, or and actually this paper shows that by increasing the number of shots in the context, essentially LMs are very strong in context learning general purpose models in this case, especially for the long context models now as well. So you can do this by actually, you can potentially discover new algorithms through this iterative way, which is essentially what I did recently here for large language model optimization. So yeah, I actually plan to use this technique more myself, and you'll see many, many more research directions using such techniques to generate code, perform in context in context learning with the code generated to perform a particular task and really do this really well. Essentially, it's a new way to do, I suppose, machine learning, but in this case, instead of training parameters, you're actually optimizing code snippets, which is very exciting. And I can see this really revolutionizing many fields, particularly where it should have things defined by code. Oh, there's another question. Yeah. So the one question, Dinesh, I would like to use LLMs to produce better neural network ML models to break the benchmarks. You can do this. I actually have a paper coming out soon on this, so stay tuned. But yeah, I think there are papers existing for neural architecture search. You can use LLMs to generate code for a architecture and then run it, and then iteratively give it back to the LLM, and it should be able to refine and actually give something quite exciting. Yeah, you could do that on Kaggle. That should be doable. Just thinking if there's better ways. The only disadvantage of that, of course, is you may actually get better performance by using other optimization frameworks rather than just a pure LLM, such as we know with RL algorithms, it's not all defined by the code. You have obviously, of course, hyperparameters, and you may benefit like from Bayesian and high parameter optimization search as well. So that would be good. Have I asked LT Mac to write a better version of himself? I haven't, no. I could do that. I'll be honest, there is real code generation startups in this space operating, which do that themselves with their tools. But this was just a research paper. We know the challenge of reading not well-documented code. Does the code generator also provide comments to explain what and why it has been done? That is a great question. That's really dependent on the input prompt you give it. It will then generate code as good as you kind of ask it to. If you ask it to generate comments, then it will obviously generate comments. If you don't, it probably won't generate comments. It does actually help the LM. There have been papers on this to generate well-documented code, really, because I suppose the LM is very much like, I suppose, reads like a human, and it's been trained on many human examples. So if you have very clearly documented code, it can have a good understanding of what's going on. And actually, documentation of code really helps in LM. So actually, that's a great thing to actually add in any code generation system, because it will then understand how to understand that and improve it. Whereas if you have kind of terse code which is badly documented, it can be difficult for the LM to actually understand what it's done before. Can you ask it following coding standards like PEP8 or Flake 8? You should be able to. Should be trained on that. But again, I mean, Flake 8 and PEP8 potentially, I mean, there's different, I don't know too much about this, but you could potentially just use open source code formatting tools to format all the code that it outputs. Because really you care about I suppose the actual code it writes rather than the particular format of how many tabs or indentation points. That's a really good point. But yeah, do continue asking questions. I'll just give a quick summary. So we looked at this talk, a brief history of AI for code generation, how we can benchmark code generation performance, and we looked at applications and agents, and we studied one particular case study of LTMAC, how to create large unbounded code bases from a single prompt. And we also looked at future research areas of how you can use LLMs for generating high quality code and iterate this within a loop to leverage LLMs and context learning ability to improve the generated code. And you can find more how to get started with such approaches on this particular website link here as well. I encourage everyone to unmute themselves, ask some questions now for the next 5-10 minutes. I would fully encourage that if there's any questions. Thank you. Or any other things that people want to know, or topics I could talk about, yeah, now's your time to ask. Oh, thank you, Adrian. Or anything that anyone wants me to go over in more detail, or even future research areas, or what I think is exciting. I don't know. I'm not sure what the demographics of people. Oh, what's this? I'm really enthused on the potential with this. Use as a companion, but also a tool. Okay, yeah, thank you. Yeah. Yeah, I mean, I'll just talk more generally about like what's coming in the future, I suppose. Research areas. We've seen, I mean, code generation has been doing quite well. We'll see in the future multimodal code generation coming up. Obviously, image understanding, and I suppose, yeah, we'll see initial works on kind of UI generation as well with images and rendering those out. Yeah. Oh yeah. Someone asked me, what do I think will be exciting? Yeah. And also someone said, is it aware of possible security vulnerabilities of each library it's using? No, actually, that's a big problem with the AI code generated. People are finding actually it's very liable to security vulnerabilities of each code library. Because if you think about it, I suppose these language models have a cutoff date, potentially 6 months to 9 months or even a year in the past. So the coding kind of standards it's using, if you just use it out of the box without any, just relying on its memory weights, will be somewhat dated. So actually a lot of the code generated by these approaches, and also it will be kind of big in a boilerplate junior code, I suppose, not expert written code, will have many security vulnerabilities in it. So actually I encourage everyone, if it is used in production environment, to always check for security vulnerabilities and check for the latest vulnerabilities of libraries. You can mitigate this by using something called retrieval augmented generation, by loading, say, potentially the latest library API specifically into the larger context windows, and even the updated security vulnerabilities. Maybe a security vulnerability came out and there was a fix for it. You can put this in the context window. It should show some understanding, but again, this is initial kind of practical things of what would be possible. Would that extend to geospatial and mapping, do you think? I'm not sure I fully follow your question, Jake. Would that extend to geospatial? What was the question before?
So you said about multimodal and like image recognition and stuff. So I was just wondering whether it would extend to like satellite imaging and creating maps and things like that.
Oh, right. Yeah, that's a good question. You could potentially. I mean, I'm not sure what the literature says about putting satellite imaging into into these image models. I mean, from my understanding, it takes an image and it breaks it into what is it, like pixels of soft token, like a image transformer. So I don't know. It depends really what it's trained on. You'd have to test that separately, whether it can understand geospatial or mapping. Potentially. I'm not sure. If you're interested in that, you potentially could in your system. I'm not sure what you're trying to do. Train some sort of image transformer model on your images to, say, give a high level signal, which you could then feed into the LM, and you could actually control that. Maybe you're trying to detect something in satellite images. You could train a separate detector with that, maybe using existing frameworks. Like a good one might be Fast AI, something like that. And then you could give that as a text output into the LM. Interested to learn more about if and how can learn based on data pattern to figure out what algorithms would be better suited. Yeah, that's a great point. I mean, I myself am not fully familiar exactly how these things learn and work to improve. So in this case, you can see, in this case, it's improving code generated output for a particular problem, especially the long context models. You can kind of ask the LM to reason why it's making these decisions and what it's saying, and it will kind of give some sort of realistic understanding. And particularly, you can do this for things like neural architecture search in a particular domain. So we looked at some things like I think medical domains and things like that, and it can kind of give semi-plausible explanations of why it's changing something to make it maybe more physically plausible for that feature to do something there. But I mean, this is again a very ongoing area of research. And maybe other people might be better suited to it, to ask questions like that. Maybe like Nabil actually on I suppose data understanding or interpretability of algorithms and why they do things. But that's a really good question. Yeah, it's not clear. I mean, I suppose one way is you could maybe think of this, why it does this, I suppose a bit like evolutionary research. You're trying many different things, you're finding what works, and then it's using its kind of in context ability to look at things that's worked before and combine them with things that think might work, and then try and iterate a new version of that. And then just because it has all these programs in context, it can continually do this, and then update that. Feel free to ask more questions. I'm keen to, or anyone wants to see anything else. I think there was one question, what do I see exciting now? I think all I mean this is very exciting. I think this in context learning ability. And actually what I'm very excited about is to do in context reinforcement learning with LLMs. Instead of just generating code bases, can we actually the LLM learn how to generate better code bases instead of just always generating code bases like a junior developer? Can we actually give feedback, and it can actually learn lessons to do various things at various times? And I think that's very exciting. But also just broadly on that, I think it's very exciting to just look at particular problems and then improve the problem by creating this LLM code generation improvement loop and analyzing that, and or giving the LLM more context. I think it's a very good general purpose kind of piece that it can do things with. And ideally, I suppose the goal is to have some sort of automated assistant that can work on your computer with you, completing work unit tasks and doing that. But I think we're at it. It's nice to shoot for something like that as a North Star, which is quite exciting. But yeah, any I suppose I'll open the floor up to Bill soon. Any other thoughts or questions, or want me to go over anything? If not, I can quickly show maybe the website, which I talked about. This one, if it works, might not work. If you go here, you'll see do Mac. And it's if you get started, or you can see the gallery example, so you can see a playable snake game, or a URL shortener, or and actually logs the IP address and timestamp, or an entire book. So this book was actually created by just one prompt, and then let it run, and that was quite nice. As you can see, so actually you gave the text as Markdown, and then I just colored it with Word, and then added images from GPT-4, which were rendered. And it's quite amazing that this was kind of done by instructions at a high level, and then each part was given. And I believe the prompt for the entire book should be here as well. Book generator, here's the entire prompt. You see, you can call generate book. But you may be interested in how do I use this in this iterative loop by running code. And if you actually come in here, and you should difficult. Yeah, I mean, I would check the dinner recipes in there. I can't guarantee they'll be safe to eat. You know, that's what the LM said. I've tested it sometimes before, and some of the failure cases might be just combine the ingredients you have. So there's no guarantee that what it says in there is at all safe. So please do check before even attempting to do anything. But yeah, you should be able to essentially run code. I'll have to find it, but you can normally just call a API, or even better, actually, would be the OpenAI cookbook example. Yeah, this is quite good. You have nice examples. Great. So yeah, I'd recommend actually for production code using OpenAI's examples themselves. These should be up to date with the API specifications. It seems they have updated multimodal and GPT-4 ones. Originally, these were I used them for my work. But if we want to do like a code generation, they also implement code searching as well, which was a thing that L2 Mac originally had, but ended up removing it just to make it quick. but you can also do things like code search. You can see, you can take a code base, split it up into parts, and then into a data frame, and then actually use embeddings to search over and return relevant strings, essentially. That should be once code testing. Anyway, but yeah, this is a great resource, OpenAI cookbook for using LLMs in particularly in production and getting latest up-to-date code snippets too. Great. I think I'll hand back to Nabil unless there's any more questions. Yeah, I really appreciate everyone's time and really excited to see what you do next with such an exciting tool.
All right. Thanks so much, Sam, for this. Yeah, I think this was like super good, and for everybody else. So Sam will be back for one of the mentoring sessions. So if you do have more questions as the week unfolds, I'm sure Sam will be back late in the week. So you can definitely catch him then. Andreas, I guess
Yes.
I'll bring you back.
All right. So thank you very much, Sam. Thank you everyone for your contributions today. So now we have our first mentorship session. Unfortunately, Paulius had to rush off and cannot make the session as planned, but we have Nabil here. I am opening the breakout rooms again, so there's some for an open chat where you can just meet up and talk. Of those of you who are in Cambridge, use it to organize where to go for a beer tonight. And there's also one that's called Nabil, and Nabil will be in that room and answering questions about his work, about the summer school, about probably lots of data-centric AI, which we will talk about tomorrow. So we leave this open for a little bit. Other things from the organization side. So I've just organized all the little exhibition pieces, so little talks that our participants will give over the next few days, so you can be excited for that. If you still want to exhibit something, we might be able to open a slot here and there for you to do, so just send me an email. Also regarding the recordings of the day, obviously the Zoom recordings take a little while to process after we're done. So I will try to get them out as quickly as possible this evening. Depending on what time they go online, I might extend the availability of those for those who've missed some sessions. And other than that, I will open the breakout room now. You can hang out for a little bit. I will probably close the Zoom call around 6-ish. And then I hope to see you all back tomorrow.